so we can get going. All right, good morning. This is Saturday, May the 22nd, 2021. We're gathered here today in Zoom to hear Kelly Detweiler talk to us about his new book, The Energy Switch. I have had the great pleasure of getting to know Peter over the last several months. A Vistage chair out of Wisconsin introduced me to him because he knew that because of the work that Guido Pez is doing, was very interested in energy and renewable energy and the impacts. And he said, you got to talk to Peter. He's the guy that knows all about this. And since then, I have taken 2 courses of Peter's, one about the electric grid. These were paid programs that I gladly got more than my money's worth out of, 4-hour segments each time, and he just kept rolling. We got, I think, a 10-minute break, but he had enough material to keep us glued to our seats all that time. And then a second one on hydrogen, which was more recent, where he had done some very diligent research. He's a very thorough researcher. So I look forward to hearing what he has to say with us this morning. And from that point, Peter, I'll turn it over to you, and screen share is on. So anytime you want to use it, it's there for you.
Thank you. It's a pleasure to be here, and I appreciate the invitation. And it's truly a remarkable group of individuals spread all over the planet. So without further ado, I'm going to jump into a relatively short slide deck that helps inform and structure the conversation. But before I do that, I want to encourage questions throughout and from anywhere. I have been in the power markets or in energy and electricity for now 3 decades, and spent from 1997, I got into retail competitive markets like we have in Australia with the AEMO, and in many parts of the United States and also parts of Europe as well, where generators compete with each other and sell into wholesale markets, and other entities buy and then sell to the end use customer. So I got into that space in 1997 with a company called New Energy Ventures, which then got bought by AES, which then got bought by Constellation, which then got bought by Exelon. Anybody who's been in the energy space, you know that every 3 years, you got to get yourself sized for a new golf shirt and your new coffee mug and your new HR policy and a difference in your 401k. Other than that, pretty much everything stays the same. And then in 2000, then I was asked to head up Constellations to start Constellations Demand Response Group, which essentially was building a virtual power plant. It was paying people not to use energy during periods of peak demand. So we had steel mills, we had concrete, rock crushers. One of our rock crushers, for example, had 10 megawatts of load in 2 separate sites. And we built an app on the iPhone where the watchman, because he was the one who came in after 4 o'clock, could actually bid that company's non-consumption into the market the following day. And it would be ready to drop 20 megawatts of load with 10 minutes of demand, with 10 minutes of lead time, in case some other asset, generating asset on the grid, were not performing. So quickly, instead of bringing a new generating asset on, instead of raising the bridge, lower the river, right? So we had this customer, the night watchman, actually bidding in from the app 20 megawatts of load every single day. And they'd only be called upon once every 3 weeks, but they'd be paid every single day for making that demand available. So by the time I left, we bought a competitor. We became the 2nd largest demand response provider in the country, and indeed in the world. I had a team of 35 people. Then we acquired this other company, so we jumped up to about 125 folks. Then Exelon bought us, and they didn't want a virtual power plant. So they were looking for somebody who wanted severance, and I'm 6'4", and on my tiptoes, I can get up to about 6'7". And I'd been there 15 years. So I raised my hand and said, fire me, fire me. And fortunately they did. And I got 3 weeks for every year I'd been there. So 15 years times 3 weeks, I got almost a year's worth of money to do nothing but think. And so what I did was I started writing for Forbes. And I interviewed about 150 people, and wrote 150 articles for Forbes.com the first year I left as an SVP and just moved into doing nothing land. And so I was able to interview the CEO of IKEA. What was IKEA doing? Why were they buying wind turbines back in 2012 to serve their demand? Why was the CEO, Peter Agnefjäll, marching in the climate march in New York? What was happening with John Young building software that eventually would manage 14 different battery systems and integrate with California's grid, New York's grid, New England's, ultimately being purchased by a Finnish company? Well, and I got to interview all the storage companies. I got to interview Lynn Urick, who's the CEO of Sunrun, which is the largest US residential solar installer. So I was able to start to figure out what was happening, because when I left Constellation, I was arguably one of the leading experts on demand response. But popping up out of that prairie dog hole, I look around the plane and I don't understand what's happening with batteries, electric vehicles, wind, blockchain, solar, everything that is going on in the space. And so I decided that I would dedicate the rest of my professional life, however long that is, trying to figure out what happens when you look at that loom and you pull on the yellow yarn. How come the blue one moves, and why, and how much? And so starting to figure out those interactions, and then the speed of the change and the dynamics underlying it. So what we're going to talk about today is how the grid is evolving, why the electron eventually in this clean energy migration that we're working on right now is the biggest thing humanity's ever collectively tried to accomplish, why the electron ultimately will dominate the energy space, not just the power grid, but move into other areas as well, whether it's in the form of green hydrogen or in energy storage, et cetera, and just talk about those dynamics and where it's all headed. So without further ado, we'll jump into the slides, and I'll talk a little bit about the process of the book, because what was great about that was it gave me an opportunity to do this inquisition, if you will. Here's my desktop here. You all can see that, right? Share. Okay, and I'll pull this up. Okay, and then we'll put this in slide view. Okay, can you all see that?
Mm-hmm.
Okay, so we'll just talk about some of the experiences I had writing the book. And when I wrote it, those of you who are involved in power markets know it's really technical stuff. You can geek out and quickly lose everybody if you want to, if you fall into the nomenclature and all the little things that we use for shortcuts and so on, and just the technical jargon of that industry. And so what I did with each chapter was I told a story about some individual or something that then I hoped would create that sort of mental Velcro and that on-ramp into the more technical conversation that followed. So I got to interview, I was going to go to Texas to a ranch where they raise Dorper cattle, Dorper sheep and Wagyu cattle, where they put 7 turbines on this property in Concho County. And I was going to go and visit someone who was building a platform. You can drive over this thing with your Nissan Leaf, just the same way you put your electric toothbrush in the stand and it charges, or the new chargers for your phone. This guy developed this technology, comes out of, he was serving in Iraq, in the army, and he was in Baghdad, and his job was to help keep one of the neighborhoods peaceful. And one of the biggest problems was no electricity. So he ended up bringing in a generator, getting the Iraqis to pay for the fuel, and putting in this pretty big generator in this neighborhood. And he said within a couple of weeks, there were wires festooned everywhere. And he didn't know anything about power when he started, but by the time he left Baghdad, he knew it pretty well. So what does he do? He ends up creating something that looks a lot like our iPad or our MacBook Air. It's about twice the size, military reinforced structure. You drive over that thing in Nissan Leaf. As you get close, your app goes doo, 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 and you're right on top of that thing. It's the equivalent of the tennis ball you drive into that hangs on the string in your garage so you don't smash into the back wall where all your paint's stored on the shelves. And then the car charges without touching anything. And now he's selling that everywhere. So I got to visit people in real places before COVID and then virtual afterwards to tell these stories, to do the chapter on gas turbines, to do the chapter on batteries, the chapter on electric vehicles, and so on. So it's a really fun process for me. And I hope it makes the world of electricity a little bit more accessible to maybe not your layman, but someone who is interested in the space and wants to understand how it all ties together and what's changing and why it's happening. So this picture here is from a ferry that I was in southeastern Massachusetts. John, you'll probably know the area, Fall River. This is actually in Somerset. So we disembarked 2 springs ago, Fall River, on this ferry. And what we're looking at here is a 307-acre site. It's the former Brighton Point 1,600 megawatt coal-fired plant, which was the largest polluter in New England. It was one of the Dirty Five, and it was the top one. And it also, before it had the cooling towers, had once-through cooling for the coal plant. And what that meant was it was pulling 1 billion gallons of water out of the bay every single day and cooking all the larvae and trapping little fish, impinging them on the screens. So Dominion, the owner, was forced by the EPA to spend money on these evaporative cooling towers. So with technology from China, they built these 2 500-foot cooling towers, the largest ones in the world. They put them in service. And then what happened? Technology came along. People figured out how to drill into shale hydrocarbons, first vertically, go down a mile, then run horizontally, and then drive 3,000 pounds of pressure and sand and surfactants into that shale with a shock wave that would open up the shale, and then with the sand, keep those pores open so gas and oil would bleed out. Well, that fracking revolution happened really fast, and it caught everybody by surprise. It caught the coal plants by surprise. In fact, if you see the graphs that show how quickly coal generation is declining, it's not wind and solar that's the villain that pushed coal off the picture and is pushing coal off the picture. It's cheap natural gas. So Brayton Point basically became uneconomic. 5 years after this $570 million investment in the cooling towers took place, they shut them down. And shortly after that, a company, Commercial Development Corporation, paid $8 million for the site, including the assumption of environmental liabilities. What were they going to do with it? Well, turns out off the entire east coast of the United States, there is now this massive effort to put in offshore wind. The Biden administration wants 30,000 megawatts. States have already made commitments of about 25,000 megawatts. New York alone has a commitment to build 9,000 megawatts of offshore wind. Massachusetts now up to 3,600 megawatts. Virginia's commitment now by legislation, I think, is 5,000, and so on and so forth. So these guys bought this site, 307-acre site, for the $8 million, and it's right there in southeastern Massachusetts within spitting distance of where they're going to build these offshore turbines. And there's only one bridge they have to get under. And it has a 700-foot long wharf with a 34-foot deep channel. So now this potentially becomes one of the major staging areas for northeastern offshore wind, sort of converting swords into plowshares. So because I wrote a piece for Forbes about this, I got invited to come onto the ferry and watch this thing implode on a windy day 2 years ago in the spring in Massachusetts. Just to give you a sense of how quickly these things change. I was invited, Smart Electric Power Alliance invited me to do a keynote for a number of commissioners, state public utilities commissioners. And the person that I work with there, she's a former Massachusetts commissioner. And she said, Pete, I want you to be provocative. When you do your keynote, if it's legitimate, throw a bomb into the room. So I basically it was virtual. And I said, okay, if you're a commissioner right now, and you're looking at approving a gas-fired plant, 500,000 megawatts, somewhere in that range, you're talking about $1 billion, north of $1 billion of investment. I can confidently assert that within 15 years, you're going to be looking at a stranded asset that will no longer be a viable asset in power markets because of the dynamics that are taking place. And we'll start to talk in the next slides about what's happening and why it's happening, and particularly why it's happening so quickly. So the CEO of Hannon Armstrong, which is a company that has billions of dollars of clean energy under management. I interviewed this guy for Forbes, Jeff Van Eckelen, and he said to me, we've never seen a time in the history of humanity that we can either make money or incinerate capital as quickly as we are going to in the next 3 decades. The International Renewable Energy Agency, IRENA, their estimate is $130 trillion of investment between now and 2050 to keep us at 1.5 degrees centigrade. And I don't know if you saw the International Energy Agency's report that just came out this past week that basically said, we've got a very narrow path to get there. We've got to stop building anything with a hydrocarbon in it almost immediately and radically increase the amount of clean energy tech we're bringing to the game if we want to avoid some really unfortunate climate outcomes. Okay, so this is Corey. I want to introduce you to Corey. She's a supercomputer named after Gertie Corey, who's the first American female scientist to win the Nobel Prize in biology with her husband. Corey is a supercomputer that sits at Lawrence Berkeley National Labs on a seismically proofed floor. In fact, there's glass in the floor. When you go out and see it, there's a glass piece where you can see where it sits on the spring. So if there's an earthquake, nothing gets damaged in there. It's air cooled, and the air moves through there so quickly that my guide stuck a dollar bill on the screen where the fan is and then left it there. And then he went back and said, someone's going to take that. So he put it back in his pocket. But he walked us around, and you see all these great computers, and they're all wired together. And what do? Well, they model, among other things, the Big Bang, not the TV show, but the beginning of time. They also do a really cool thing for clean energy. Let's say you have a wind turbine and the 3 megawatt machine. That tip of that blade is rushing through space at roughly 210 miles an hour. And it's supposed to last 20, 25 years. Well, over time, with rain, hail, dust, insects, that leading edge of that wind blade gets pitted, and you start to get friction losses that add up over time into percentages. And you're spending millions of dollars up front for these things, so it really matters. So you say to Corey, I have this problem to solve. Or let's say you've got solar panels sitting outside of New Delhi, or it could be in China with the air quality issues. Last year in New Delhi, when they were burning, the farmers were burning the crops and the stubble after the harvest, the air quality was so bad that kids were kept indoors. And there were great pictures in the international press from a visual perspective, but horrible if you were breathing that air. Well, if you're a solar panel sitting there, that stuff's coming down out of the sky and sitting on the glass on the panel and starting to really impede the ability to convert photons into electrons. But what if you could make a glass so smooth from a nano level, from a molecular level, that essentially particulates would slide off like snow off of a cold windshield? Well, or make a better battery. Well, it turns out if you have an idea like that, you go to the researchers at Corey and say, here's what we're trying to solve for. And there are 22 nations involved in this thing called mission innovation. And what they do is they look at your value proposition, and if they like it, they assign you sort of a guide dog, if you will, and they help you build the code. And then you go to Corey, and what you actually do is send her loose into the periodic table to grab all the constituent elements and start to combine them in every possible way that might solve your problem, to create new compounds, theoretical compounds, molecules that have never existed in the history of the planet. And she comes back after a week or so. She does 30 quadrillion calcs per second, so she's not too shabby at that, and comes back and gives you a rank order list of, say, 150 or 200 new molecules. So I was telling a guy a physicist on the airplane about this when I was flying one day to a business meeting, and he looked at me and he said, yeah, but it takes 2 to 3 years to now synthesize those because there is no recipe for a molecule that's never existed before. So how do we make it? Well, they're solving that problem as well. When I was interviewing Kristen Person, the scientist, the PhD scientist who runs Corey, she said, you ought to talk to this guy in the UK because now what they're doing from a synthetic perspective, they're enlisting robots. And the great thing about robots is 2 things. One, they don't get tired, so they can work 24/7. They never go on strike and they never demand higher wages. The second thing is they don't feel shame. So failure is not an issue for a robot. As Kristen Person said to me, you'll never see the Journal of Failed Scientific Experiments, but you can find that with a robot. And the beauty of that is the robot's churning through all the stuff, trying to make stuff. Well, it's documenting the failures just like it's documenting the successes. So now it's laying down all this information that can then be combed through to figure out how to get better at the process of synthesis. So at a global level, what's happening right now, by the way, this machine, they told me not to get too attached to her. I went to the next room and there was this ginormous empty cavern, concrete gray cavern. And turns out now it's being readied for Perlmutter. And Perlmutter is actually, he's alive, a scientist who's alive. It's named after him. That thing's going to be 4 times faster than Corey is. And they told me now they're having, in fact, they were talking about the scientists from Australia on Christmas Day, after Christmas, it was still Christmas here, them pinging, trying to get information. And they hadn't set everything up to share. And now they said, we have so many people trying to get the information because it is all publicly available. It's paid for by governments, that we have had to outsource it all to an entity like AWS, Amazon Web Services, because there's so much data we now have created that people are pinging into, that now we've had to create this massive database and offshore it from our facility. So what do you end up with? You end up with things like spatial atomic layer deposition with better research, better capabilities. You end up with China's contemporary Amrex technology, the largest battery company in the world, that just announced last July that it's building a new campus, 40 acres with 1,000 scientists with PhDs, battery scientists, material scientists, to investigate all kinds of battery chemistries, not just lithium ion. You have them saying, oh, we now have a battery pack that can take a car not 200,000 miles or 250,000 miles. Ours can go 1,000,000 miles. So instead of 2,000 or 3,000 cycles, we can give you 10,000 cycles, maybe soon 15. Tesla's research chief, Jeffrey Don from Dalhousie University, says, we think we can come up with a chemistry that'll give you 2,000,000 miles in a car, and you'll never need it in the car, but you will need it when vehicles start to interact with the power grid. And we're starting to see the first instances of what's called V2G technology. VW says all their vehicles next year will be vehicle to grid capable. That is not only intelligently pulling power from the grid at the best possible times, but at other times releasing energy back to the grid when it's needed, whether it's to maintain the frequency stability or more energy and like what you just saw with Ford with the 150. I don't know if you saw that announcement. The Ford F-150 has 110 kilowatt hours or 150 kilowatt hours, depending on which size. And now if you have a power outage, all you do is you plug the charger back into the F-150 and it ties right to your electrical box. And now you have power for your home for the next average house is 30 kilowatt hours a day. So the small battery can do 4 days and the big one can do roughly 5 days. So now the vehicle and your house start to become a unified ecosystem. And guess what they did? They tied in with Sunrun, the company that puts the solar on the roof and is the leading solar installer. So now you start to see this home ecosystem evolve where you have solar on the roof, maybe a battery in the basement, and then another battery that's rolling around on wheels all the time. That's where this is heading, and it's heading a lot faster there than most people really believe that it will. Here's another thing. So just to, again, give you the sense of pace of change. So you can see the little guy down there in yellow in the vest. This is the Wind Technology Testing Center. It's right outside of Boston in Charleston, and it sits along a wharf, so you can bring blades into the harbor. And this thing was designed in 2011. I first had a chance to look at it again for a Forbes piece about 4 or 5 years ago. And then I thought, oh, this would be a cool section for the book. So I went back there and I talked to the lead technologist, and then I talked to the folks who designed it back in 2011. They said, so back in 2011, we were looking at roughly 1 megawatt turbines. And the biggest, longest blade at the time, these are composite blades, was roughly 50 meters. So we put together this facility, and what it does is they put the shed for 90 meters. What it does is you basically put these forms on it, like you can see there, that thing in yellow and black. That's essentially a plywood form that matches the blade, that then they put, it has weights on it, and they move the weights back and forth. And so it vibrates the blade up and down, causes it to oscillate. Over a 6-month process, a blade for a 2 or 3 megawatt turbine could be tortured 1,000,000 times in one direction, 2,000,000 times in another direction, and then some torsional twisting as well. And then there's strain gauges up and down the whole thing like an EKG on your head. And then over on the right, you'll see those windows over there. There's a whole bunch of computers in there, and you just walk through and you're seeing the sine waves just consistently with every vibration. And what they're doing is they're simulating 20 or 25 years of outside environment. And then at the end, the cool thing is this thing has 165 foot of rebar and concrete into the earth. And first of all, it's to manage the stress of vibrating all these blades, 3 at a time potentially, over the million, 2 million, 3 million vibrations. But then it's also meant to deal with what they call test to failure. And test to failure, what they do is they put steel cables around the blades, and then they start to inexorably winch that cable down and down and down because they want the blade to explode. And so they have high-res cameras all through the site. And essentially that blade bends and bends and bends, and at some point it gives. And I asked the lead engineer, pretty sober guy, as most engineers are, so what happens when that thing finally does fail? And this big smile creased his face, and he said, oh, it's one of the best things you ever saw. The release of kinetic energy is unbelievable. He goes, see this glass here? And the glass you see over on the right-hand side, he says, that's 5 inches thick. That is bulletproof glass. And he goes, sometimes they just crumble, but other times stuff explodes and flies all over. He said, one time, he said, you know how you went through that guard shack? It's about a mile away under the Mystic Tobin Bridge. He said, you remember when you drove through that shack? I said, yeah. He goes, one time they actually called us from the shack because the report was so loud, they thought something had exploded inside the facility and they wanted to see if we were okay. So 50-meter blades designed 90 meters. This year I go back and I walk in and he takes me for a tour and he says, see that blade there? Notice anything unusual? And I look, and sure enough, the end of the blade is sawed right off. It's the GE 12 to 14 megawatt turbine now, not the 2.5 megawatts, which is the average in the United States installed last year onshore. These are the behemoths going offshore. A 12 megawatt turbine from GE can be extensible to 14, has a 107-meter blade. So they had to cut off the last 30 meters just to get it into the facility. It was just announced by Fraunhofer last week. They're putting a 116-meter testing facility in Germany. When I talked to this guy, Raul Yarrala, who headed this up, I said, all right, so you made the shed too small. And he goes, well, nobody saw this happening so fast. I said, well, what about the future? He goes, oh, the next challenge is this. So right now, we know we're going to put in a lot of these 12 to 14 megawatt machines. In fact, Siemens Gamesa just announced a machine that can go up to 15 megawatts, and they did GE one better. Instead of 107 meters, now it's 108, right? Just a little bit of a tweak there. Well, these are all for fixed structures. These are the classic towers you see coming out of the continental shelf, the shallow ocean floor, or the jackets, which are like steel triangular structures, but they're fixed. And a fixed structure means when the wind is blowing, you're basically imparting all the stress onto a fixed structure. But what if you float the thing instead? And that's the next phase of offshore wind, which is going to dwarf what's happening with these fixed structures. Offshore now, they were already testing a couple of 8 megawatt machines and commissioning the first ones. And Yarrala said to me, he said, we don't know how big those are going to be. They could well be 25 megawatts or bigger because they float on a spar that's tethered to a weight on the ocean floor. And now most of that stress is imparted to the waves, to the water. And so we can build much bigger than we're building right now. So conceivably, we see these things getting off of California and Oregon because there is no continental shelf there. So the first offshore land or space that's being commissioned right now, where the licenses are being offered by the Bureau of Ocean Energy Management, or for floating turbines. Same thing's happening. China's making a big push into it. Korea just announced they're going to do 8,000 megawatts of floating offshore wind. So this is the next new frontier. The thing that's going to tie into that, which we'll talk about a little bit more later, is hydrogen. You're starting to see a lot more of these massive mega turbines, and Ørsted, the big Danish developer, just announced they're going to tie 2 3.6 megawatt turbines, smaller offshore ones, to 2 megawatts of electrolyzers to generate hydrogen starting. The project commenced construction this week. So now we're starting to see reality take shape on the whole renewables to hydrogen. Small, but there are already 228 projects worth $300 billion that were identified by the Hydrogen Council in the report they released about 3 months ago. So pace of change across the entire industry. Onshore, the turbines will get bigger too. Among other things, the limitation right now is the Eisenhower highway system, because the bridges are 16 foot high. And the cord of that blade, this part right here that you can see where the wires hang, the thick part, the cord doesn't fit under the bridges anymore. And so now Lockheed is looking at building a dirigible that potentially could fly the blades across the landscape, because they don't fit on trains and you can't put them on a flatbed truck. And so, and they're also looking at, GE already has a composite blade in 2 pieces. So they ship the parts and then put them together. Their 5.3 megawatt Cypress onshore turbine is a 2-piece system. And now there's a company in northern Texas that's building spiral welded on site, the same way if you ever had gutters made for your house where they actually roll the gutter right at your house, that they have the roll of aluminum there and then they roll it out and put it on at your house. Same thing now. They're trying to get these tower heights from, say, roughly 80 or 90 meters up to 120, 130, because wind is a function of the cube of the wind speed. So 10 miles an hour versus 20 gives you 8 times as much energy. And that's in the better aeolian currents are higher up because you're getting away from the topography of the planet. And so there's whole parts of the country like southeastern United States that are not economically viable for wind at 80 meters, but become viable at 110. And so onshore, that's what we're seeing. There was a really cool piece I saw about, I don't know, 5 or 6 weeks ago. Ed, you probably remember it. I do this weekly video on LinkedIn, and I had it in one of those, where in China, there's a Spanish company that has a telescoping wind tower where the parts are inside of each other, and there are winches built into the tower that raise the interior sections so they can get up into that 150 meter range, which a crane simply is not large enough. No cranes in the world are that tall, can't do that. So it has to be a self-leveraging system. So a lot of work being done in that area because the best free fuel is high in the sky. So here's just the cumulative wind power capacity growth. You can see it's not a steady curve, and that's all driven by taxes. So in 2012, there was a huge amount of wind because the production tax credit was about to expire. That lasts for 10 years and gives you roughly 2.4 cents a kilowatt hour. So everybody, it's kind of like last call at the bar. You run up and you grab as many beers as you can possibly carry on your tray. And then so in this case, everybody went to the bar, built all that stuff. So there was eligible for the credits. And then the hangover in 2013, almost nothing got built. Same thing we saw happen in 2016, 2017, the PTC, the production tax credit, and the solar investment tax credit got extended, but everybody thought they weren't. So there was a rush to get a whole bunch of stuff built then. And now we're on a little bit more of a steady trajectory, but the production tax credit and the investment tax credit for solar are now set to decline again, although the Biden administration is looking at some extensions of those. So it's very much tax credit driven, but nonetheless, you can see that over the last decade, we've really seen significant growth from, say, 40,000 megawatts of wind installed to now 122. And there's another 40,000 in the construction pipeline right now in advanced stages or advanced financing. So wind is really still going great guns. Texas is the 5th largest renewable energy economy on the planet, and pretty soon will be number 4 because they're going to add as much solar in the next 5 years as they have wind now, probably. But you can see Oklahoma does pretty well, Kansas does pretty well, Iowa does pretty well. Oklahoma gets, and Kansas, I believe both of them get more than 35% of all their electrons from wind right now. Texas is a lot lower percentage-wise because it's a much larger economy, but nonetheless, pretty robust market in those states and nothing in the Southeast, in part because coal generation had been relatively cheap and because the wind regime is just not that good until we build those taller towers. Here's what got installed last year. Again, Texas, a world leader, but you can see the Midwest did pretty well. Wisconsin, no, but Minnesota has some really huge turbines up near Lake Huron on the thumb over there. And Illinois certainly did a lot. Iowa is actually looking at a multi-billion-dollar transmission line to bring gigawatts of wind energy from Iowa along a railway right-of-way to the markets in Illinois close to Chicago, where they're going to underground the whole thing. And that may be one of the new dynamics we see in the system is we have these huge pockets of free fuel all the way down the spine of the United States from North Dakota down to Texas, and then another huge pocket of free fuel in the southwestern United States in the form of sunlight. And if we could transport that fuel, it would be cost effective to do that rather than trying to generate in some of these other places where the wind doesn't blow as hard or the sun doesn't shine. So one of the things the Biden administration is looking at right now is that federal highway system and the rights of way along those systems, because the roads link all of our major metropolitan areas, which happen to be our load centers, and they generally traverse empty spaces, which in many places happen to be where the renewables are. So there's a lot of discussion around the fact that we haven't been able to build large-scale transmission overhead because of NIMBY issues and rights of way. But along the highway system, the states have the final say. They actually own the land, but there's a greater ability to coordinate what might happen across the highway system. And we might see within the next decade, massive high voltage DC lines undergrounded, moving large currents of power from point A to point B. Here's what's in the pipeline. You can see Texas still has another almost 5,000 megs built. Again, a lot of this is happening in the red states right up the middle of the country because that's where the fuel is. Again, Wisconsin conspicuously absent, although there's 1,100 megs of solar coming into the state with Alliant, with your utility there. Solar, a similar phenomenon, but really that party only got started in 2010, and now it's grown considerably in the US, but not just here. Australia has over 2 million residential rooftop solar installations. In fact, in South Australia, there is so much rooftop solar that from the hours of 10 o'clock in Q1 of this year, from the hours of 10 o'clock in the morning till 3 in the afternoon, the average market price for electricity in South Australia was negative $12. That is, you had to pay somebody else to take your power. And there was so much solar that for the first time, the state actually shut off the ability to export power from residential rooftops into the grid because it was destabilizing the grid. So there's a whole lot of need for energy storage in many markets. Australia has a lot of energy storage. Germany now has over 250,000 batteries behind the meter in people's homes. That's happening on a large scale in the United States as well. But you can just see how quickly this dynamic here is happening, not just here, but Germany, Australia, other places around the world and some of the leading markets. Here's what's projected. So you can see historically in the past, and then from 2021 and forward. This is from Wood Mackenzie and the Solar Energy Industries Association, just for this country. But these trends are analogous in a lot of other places. It was just announced this week that in Spain, they're going to do this really cool solar project with hydrogen. They're going to take solar. They're going to use the solar with electrolyzers, and it's a 20 megawatt project to crack water, separate water into H2 and O. Then they're going to use the hydrogen for 4 hours of storage and essentially to sort of flatten that curve. And with the reverse osmosis, they're also going to clean up the water. And they're going to generate hydrogen for transportation and industrial applications. So solar, as it gets cheaper, as more volumes come on, they're also not just looking at offshore wind, but solar is another potential application for hydrogen. In Australia, in the Pilbara region, in the Western Australia, there are some massive 10, 20,000 megawatt types of renewables projects, wind and solar, with electrolyzers being planned for creation of hydrogen and then export to Asian markets. So there is the possibility, this was Wisconsin with its 1,000 megawatts, 1,100. So there is the possibility within a very short period of time, let's say the next decade or so, if the electrolyzer costs continue to fall, if solar panels continue to improve at roughly 0.5% per year in terms of their ability to convert sunlight into energy, if wind turbines get more powerful because they're taller and more efficient, and the blades are lighter and more robust, there's the possibility we might start to see the emergence of global energy centers based upon concentrations of wind and solar, the same way today's energy centers are based upon concentrations of hydrocarbons, and that we could see these emerging hydrogen centers like that. Saudi Arabia, with their new model city, NOM, the NOEM one that they're building, they've said, we intend to become the Saudi Arabia of hydrogen. With all the abundant sunlight in the desert, we're going to put in massive arrays of solar, and then we're going to export that to Europe in the form of hydrogen. Morocco's exporting, there's a massive plan in Morocco to export gigawatts, not in hydrogen, but electricity. So putting in the desert, massive solar arrays, and then subsea cables all the way up to the UK. A multi-billion-dollar project that was just announced about a month ago. Now, not all these will get built, but some of them are certainly going to make it past the spreadsheet into the real world. This slide here is from NextEra. If you ever have time, and it's limited time, the one companies whose quarterly presentations and investors presentations I never miss is NextEra's, because they're the largest renewable energy developer in the world. And they're also this year going to install $1 billion worth of energy storage, over a gigawatt, so over 1,000 megawatts. In fact, they said on their quarterly earnings call about 3 quarters ago that they were going to put in enough storage this year that it could power the entire state of Rhode Island for 4 hours. And so in their most recent investors presentation from May 10th, just a couple of weeks ago, they have a couple slides for the first time dedicated to hydrogen. And when NextEra, which is the most profitable US market cap growth company over the last decade, they compare themselves to all their peers, and it's a joke. They're not even close to anyone else. They're so ruthlessly efficient. I've talked to people who've gone down there. He said, Pete, they have a spreadsheet with 3,000 line items, and every one of them has a cost target. They are disciplined beyond belief. And I've actually done a little bit of consulting work for them. So when they say things, I pay attention. So I have their quarterly call often on my calendar, so I know when it's coming and I can pay attention. I usually read the transcript because I can read that in 15 minutes instead of listening for an hour and a half. But this slide, the critical takeaway here is quite simple. Starting at the top, near firm wind in the best places in the country, but other places in the world, $20 to $30 a megawatt hour, levelized cost of energy. Levelized cost of energy means upfront capital cost, interest carrying cost, operations maintenance, and decommissioning. $20 to $30 for near firm. Near firm means the wind turbines plus 4 hours of duration of energy storage. So you can shift that output and flatten the curve from that wind turbine. Near firm solar, again, 4 hours, and almost everything NextEra is putting in right now, especially in solar, has a 4-hour battery adder. In fact, they're going back and retrofitting a lot of existing solar plants because the cost of installed solar has fallen by 50% in the last, the cost of installed storage, batteries, has fallen by 50% just in the last 2 years. Not because of volumes in the power grid, but because of the volumes in the electric vehicle space. In fact, China's announcing a gigafactory right now on a cadence of 1 a week. And we are announcing one in the United States on the cadence of 1 every 4 months. Although Ford just announced a 60 gigawatt hour factory, they're teaming up with SK Innovations. They just announced the same day they rolled out the Ford F-150. So there's actually been 2 gigafactories announced in the United States in the space of about 6 weeks. Natural gas, new plant burning fuel with fracking, today's cost, 30 to 40 bucks a megawatt hour. None of these have externality costs, no carbon tax, no nothing. So this is just sheer raw economics, assuming just pure plant, nothing else. But existing coal costing more than a new natural gas plant costing more than a new near firm solar plant with 4 hours of storage and costing more than the wind. Existing coal, existing nuclear. That's why those resources are destined for the ash heap, because they can't compete even against their existing competition, let alone new stuff coming into the market. And then the one flaw that NextEra has is their offshore wind price. They tend to dislike offshore wind. They think it's pretty expensive. Those numbers are coming down. The 30 megawatt facility, Deepwater Wind, that went into Rhode Island about 3 years ago and used the Haliade turbines that GE bought from Alstom. Those were 6 megawatt machines. They put 5 of them in. The contract was inked for $244 a megawatt hour, so 24.4 cents. Now we're seeing contracts in the the Vineyard Wind, Mayflower Wind was $58 a megawatt hour, 5.8 cents, so about a quarter the price. And in the UK, there's a 3.6 gigawatt facility being built on the Dogger Bank where prices are under $50 a megawatt hour. So NextEra tends to be a little bit harsh in terms of the levelized cost coming out of the offshore wind arena. In this country, it has been somewhat higher because we've been having to import everything from the North Sea experts. All the oil and gas companies up there that saw the writing on the wall changed their names and then took their oil and gas offshore platform expertise and plowed that into building offshore wind. Now that entire supply chain is migrating to the United States East Coast because there's almost 30,000 megawatts of projects on the books. That kind of scale is roughly $70 billion. Actually, it's a little bit more than that. And that will excite any investor. And so, in fact, way up the Hudson, all the way up in the Port of Albany, they're making a multi-$100 billion investment in a 5-shed offshore wind tower facility where they're going to be rolling the steel and then taking those things down the river on barges and putting them offshore. So the money's already coming into building infrastructure here in this country. Here's that lithium-ion battery slide. Bloomberg New Energy Finance, one of the better analysts in the space, just showing both offshore and onshore, and then solar costs, how much they've fallen, but that decline not nearly as steep as batteries. There's this thing some of you may be familiar with, a phenomenon called Wright's Law. And Theodore Wright, back in the early part of the last century, when airplanes were starting to being built in volumes, he noticed that the cost of labor inputs into manufacturing airplanes fell by roughly 10 to 15% with every doubling of global output. It's also called the experience curve. The experience curve with solar is roughly 23 to 28%, depending upon which years you're looking at. That is, with cumulative doubling of output, costs fall by that much. And in the battery space, very similar experience curve. Wind, not the same, because batteries and solar modules are all about modular volumes, just making more of those things. Obviously, yes, the chemistries get better, but wind is about bigger. So it's a different scale issue. It doesn't quite have the same Wright's Law type of approach. So here's what's being deployed right now for storage in the United States. As we get more and more renewables coming into power markets around the world, it's not that hard. We thought that the limit was going to be 5 to 10% integration of renewables before we'd have to add other resources into the mix like storage. What we found is, because we could change the way gas turbines worked, we could digitalize them, and the newer turbines coming out of companies like Mitsubishi and GE. For the book, I got a chance to go to Schenectady and interview 10 of GE's leading turbine engineers for 7 hours, including their lead hydrogen guy and one of their leading planners for their combustion turbines. And they said the critical thing, Pete, is you've got more and more of these renewable resources coming in, these variable energy resources. And so their output goes up and down all the time. And they need to be balanced by something else. And so what we found is our capacity factors, the utilization factors of our power plants around the world starts to decline as more low-cost renewables come into the grid. But we're asked to cycle those plants more frequently. in order to compensate for the variability. And so the market started to demand a lot more flexibility. And so the real critical thing we did with our turbines, besides digitalizing them so we knew how hard we could ramp them up and down and how much we could cycle them, was we figured out how far we could put them down in turn down mode before we had to shut them off. And the thing here to understand is, if you have a situation like California or Australia, where you have all kinds of solar panels cranking out electrons in the middle of the day, you're taking your gas fleet, which was running pretty hard at night, and cycling those things all down to a minimum level. But you don't want to turn them off, because if you turn them off, then you have to start them up the next day or the next time they're called upon from a cold start. And they have fixed ratios of how many megawatts they can give you in a certain hour. And these things run hot enough to almost melt steel. The leading turbines, which are now 64% efficiency, the one in Bouchon, France, that GE has, is coated with ceramics, so it won't melt the blades. And so you're running this high temperature, high pressure gas through a turbine. It's coming out the backside faster than a hurricane. And if you're ramping this thing up and then turning it off and starting it from a cold start, you're expanding all that steel, and then it cools down and contracts. Every time you do that, it's like a cycle on a battery. You only get so many of those relative to your run hours before you have to take the thing out of commission and refurbish it. Sometimes refurbish the entire rotor. But what we figured out how to do over time is drop the turn down mode so that now we can get down below 30% and still run within our emissions windows. So NOx and SOx, the Dr. Seuss pollutants, nitrous oxide and sulfur dioxide. And so the more flexible those turbines are, and the more we can push them into turn down mode where they're idling, but they're not using a lot of energy and they're not emitting a lot of pollutants. It's kind of like your Prius. When that thing goes into pause mode at the stoplight, the battery takes over, right? And you're not burning any fossil fuel whatsoever. In this case, with turn down mode, you're still burning fossil fuel, but you're not burning nearly as much of it, and you can go lower so you're ready to ramp up again. So with turbines, you can get about 30% renewables into the grid without any challenge. And this we're already seeing. Maui, for example, is now at 50.8%. They've added some batteries, but only recently. Kauai is at getting into the 70s and shooting for 80%, but they have some pump storage and they have a little bit of biomass. So they have some dispatchable load they can move, dispatchable generation they can move around. But if you don't have pump storage and you basically just had, say, gas fire gen, you get to 30%. Okay, beyond that, now you start to have to add the batteries, and you do it for two reasons. One, because you need that flexibility. Two, because you have so many renewable resources coming into the grid, you have this ugly phenomenon called negative covariance. And that is when the quantity of solar increases, the value of the output decreases because all those arrays are dumping energy into the grid at the exact same time, therefore creating declining value. And as we saw in Australia, or talked about before, actually negative value. But if you have a lot of batteries, you can essentially sop up all that power at a low cost. Or if you were in Australia, you could have been paid for Q1 on average over those 5 hours. Every single day, you could have been paid $12 a megawatt hour, absorbed as much energy as you could have, stored it, and then released it in the evening when prices were high and the sun had set. So once you start to add 4 hours of batteries, and that's typically where the sweet spot is with lithium ion batteries that are coming from price reductions and better technologies from the electric vehicle industry, you add those 4 hours of batteries. Now you start to look at a grid where you can integrate 50, 60, in some places 70% renewables into the grid, especially if you have nighttime wind complemented by daytime solar and a fairly constant regime around the year. So that's sort of, grid 1.0, the way I conceptualize, is pre-renewables. Grid 2.0 is you get to this 30% threshold before you need the 4 hours of storage. Grid 3.0, you start to need, you need those 4 hours of storage, and you start to see the first 8 to 10 hours. And in fact, last week we saw Highview Power, which is this company that takes air and liquefies it. And then when they heat it up again, it expands 700-fold and spins a turbine. They just announced a huge number of projects, gigawatts of projects that are coming online, giving you roughly 8 to 10 hours to 12 hours of storage. And there's other companies. There's one company, Gravitricity, that's looking for mine shafts. There's one in South Africa that's 1.2 miles deep. And they want to suspend a weight in the mine shaft, and they raise it up when there's too much energy, too much solar in the grid. They'd essentially crank it up and absorb energy. And when there's not enough, they'd lower that weight and spin a turbine, spin a motor essentially, and drop that weight further and further down into the shaft and release energy back into the grid with roughly 70% round trip efficiency. So, and there's a whole host of other technologies out there in that sort of middle duration storage range. That'll get you to your 60%, 65, maybe 70. And then if you want to fully decarbonize, you've got to go seasonal storage, taking from certain times of the year and moving to others. And right now, the only way we know how to do that conceptually is if we can get to cost-effective hydrogen. So here are the numbers for storage. You can just see they're expected to grow quite dramatically. This is just the United States, but Australia is going to follow a similar curve. The UK has some really great programs for batteries. China's starting to get its act together with energy storage as well, but the US will be the single largest deployer over the next 3 or 4 years based upon most of the forecasts you see out there. And this will be a roughly $6 billion annual industry by 2025. Oh, there it is, 6.5 billion. Almost all this lithium ion. And then you start to see these fascinating use cases. My favorite one, again, from German company Sonnen, but in Australia. So I interviewed this fellow last year, and he's a tech geek, and he's a journalist in Australia. And I got in touch, Sonnen put me in touch with him for a Forbes piece. And his name is Stephen Fenech, F-E-N-N-E-C-H. He owns a Tesla. And he moved into this housing development with 1,000 houses in a new housing development. If you go into the housing development, depending upon the size of your family, you can order one of 3 different size homes. And every single home has one of 3 different types of configurations of solar plus a battery. And so the solar sits on the rooftop, the battery goes in your laundry room, or you can see this one here. This is in the Wasatch Range in Utah. That thing right behind the lamp with the little green circle in it, that's your battery. That's not your refrigerator. And that's a lithium iron phosphate battery. So it's a pretty stable battery with a high thermal runaway temperature, so very unlikely to catch fire. And with these folks in Australia, what they do is they pay their roughly 18 or 20,000 Australian upfront, 13,000 US, let's say. And then they pay $40 a month to Sonnen. And I said to Stephen, I knew what the answer was going to be, but I had to ask the question. So what about your utility bill? And he laughed and said, I've never seen one. I don't even know who my utility is, and I don't care. Because Sonnen gets the bill and they pay the bill. And then what they do with that battery is they look at the wholesale market. They're interacting with the Australian Energy Market Operator, AEMO. They know what the prices are for frequency regulation, keeping the grid at 50 hertz in Australia, 60 hertz in this country. Japan's 50 in part of the country, 60 in another. And essentially, so they're selling frequency regulation services in, they might be selling longer duration capacity into the market. They're facing the wholesale market, aggregating all these batteries behind the meter and selling those services back in. So that's one of their profit centers. And this guy, I said, so you pay $40 a month? He goes, yeah. He goes, but I also charge my Tesla for that $40 a month. So I'm actually cost negative because I'm not getting petrol at the pump anymore because I've got my EV. So he goes, I'm actually way ahead of the game. So the next thing they were announcing, not yet for public consumption, was a 5,000 household new housing development. Again, all this going to be aggregated. So this project here we're looking at in the Wasatch Range with Sonnen, this $34 million project, 600 residential upscale units, solar on the rooftop. Every unit has a battery, $12 million for the batteries. And then Rocky Mountain Power is paying $3.27 million because they want to utilize those batteries to stabilize the power grid. So they pay Sonnen, they send the signals to Sonnen, and Sonnen, it's 12.6 megawatt hours of batteries. They're flexing those batteries at the beck and call of Rocky Mountain Power. Now they have another project like that in California, Sunrun. the company I mentioned before, they have a 20 megawatt contract with New England's grid operator. There's another group, not Sun and what's the name of it? I'll think of it in a minute. They have an 85 megawatt, Sonova has an 85 megawatt contract with ISO New England, with our grid operator, again, to aggregate batteries from tens of thousands of households and sell those services into the grid. And Sunrun now has 10 contracts worth $50 million to sell services from the batteries behind the meter into utilities around the country. So that's where this is all headed. And pretty soon your vehicle will be a piece of this. And obviously the resilience and reliability piece. So all of you probably watched, as I did, in horror as the Texas debacle unfolded, 110 people or more dead from a grid that was 4 minutes from total failure, where they were 4 minutes into it. If they'd lost another 4 minutes, their frequency they wouldn't have been able to maintain the frequency, then it would have been a total blackout. The concern in Texas was that equipment would have been damaged. Some of the people are saying, no, it wouldn't have been that bad. Saying, oh, we had black start capability. That is those diesel generators that sit there at the power plants and you crank the diesel, restart the power plant. Well, turns out 60% of those diesel units were not functioning. So we didn't have the viable black start capability to restart the power grid in Texas if it had gone down. Plus, we probably would have damaged transformers and equipment, which means arguably we were 4 minutes away from taking the 9th largest economy on the planet and removing that sliver of the pie for at least 3 to 4 weeks in the middle of the winter, taking the Houston Ship Channel out of the global economy, taking the fertilizer supply out of the US economy, removing most of our major gasoline refineries out of the United States economy. And so that would have caused a global economic ripple. And we probably would have seen many thousands of people die because cell phones wouldn't have worked for a month, 3 weeks. There would have been no communications capability, no ability to pump gas. So we take the Superstorm Sandy thing where New York was blacked out for roughly a week and put that on steroids across an entire 9th largest economy in the world. That's how close we came. This slide here is from a customer, Sunrun. You can see the solar panels on the roof. They had a battery that served all their major equipment downstairs. And the guy actually was quoted as saying, I took my dog for a walk and that's when I realized the world was dark, because he'd been completely isolated from it. One of the other guys on the call said, oh, my battery switched over. The power went out Sunday in the morning, like 1 o'clock or something. And his battery system switched over and he burned through all 4 hours of the battery before he even woke up, because his battery was smaller and he hadn't set it up to do what it needed to do in the event of a power outage. So it tripped as it should have, but didn't give him the power that he wanted to. I talked to another guy when we had Hurricane Maria rip through Florida. He had a whole bunch of solar panels on the roof and a battery. And he said, I was within 100 miles, the only person in Florida for about a week, because everyone else had evacuated. And I didn't have enough energy for my battery to run my AC, but I could run my fan, my security lights, and I had all the cold beer in the fridge that I needed. So now you're starting to see in California, after those fires and the forced outages from PG&E out there, Pacific Gas and Electric, there were estimates that there were going to be as many as 50,000 behind the meter storage units put in, batteries, just last year alone in California. And there's a couple police and fire stations now that are putting in these little microgrids with the solar and the battery and then diesel gen, but the solar and the battery are meant to make the diesel gen last a lot longer. Instead of running through it all in a week, you might get 2 weeks out of it because you're supplementing and reducing the amount of diesel you'd have to burn. So microgrids are going to be another big phenomenon we start to see as the grid gets increasingly brittle with more climate change events. And then we have this next thing going on. I mentioned before the V to G. So the first place we'll see vehicle to grid is probably going to be school buses. Montgomery County, Maryland, just announced about 2 months ago, they're leasing 326 of these school buses. And they're all vehicle to grid capable. So they'll drive, 6 o'clock in the morning until 9. And then they will basically look at the power markets and figure out when to charge. And as more solar comes into the grid, you'd essentially want to charge in the middle of the day and absorb that solar. And then they'd run again in the afternoon and carry their students around. And then in the evening, look at prices again. Probably what happens in Maryland is prices are cheaper overnight. So the battery absorbs all the energy at night, then does the thing with the kids, then sits there on the lot in the middle of the day, which is where the demand curve still is in Maryland, looks at the grid and is selling services into the grid in the middle of the day, and then does its thing with students. And then that software looks at the grid and figures out what's the optimal time to charge that evening. So again, 326 buses now, batteries capable of doing this. In North London, there's a fleet of 20 double-decker, the red ones, buses up there doing vehicle to grid every day right now. So it's just starting, but a lot of companies are articulating that they think there's going to be a pretty big value prop here, because if you took every vehicle in the country and electrified it in any given economy, you'd see roughly 20 to 35% of all the electricity that we consume today added to the grid to help move cars around if you fully electrified the fleet. That's how big the energy consumption of an electrified fleet could be. So if you had 25 to 35% of batteries on wheels of your total grid, there's a tremendous opportunity either to screw things up royally if you charge at the wrong time, or to help to balance it all out. And just to give you a sense of the size of these chargers, so Electrify America, that's the Volkswagen Diesel spinoff. After Volkswagen Dieselgate spinoff, after they got caught, they had to set up in the United States the subsidiary that promoted electric vehicles. So Electrify America now has these two necklaces of chargers across the United States, one from San Diego to Jacksonville, Florida, and another one from LA to Washington, DC. And every 70 miles or less on the highways, there's a group of charging stations. The fastest ones are 350 kilowatts. That probably doesn't mean anything to you, most of you. Go to your average grocery store, the one with 20 checkout, 30 checkout counters, that's a 350 kW store for its maximum draw. So a single charger into a car would draw as much electricity as a decent sized grocery store. That's how big these things are. Now, right now, most vehicles can't absorb that level of charging capability. The Nissan Leaf Max is like 50 kW, but the next gen, Porsche is developing a 400 kW, 800 volts. In fact, there's so much energy, they have to be liquid cooled to get this done. So that's where this space is all headed. So now if we think about it, I'm getting to the end here, and then we'll open it up for conversation, questions, which I should have done more as we were moving along. But this is a slide from Stanford. I think it's Stanford, one of the California universities. They put this out last year, middle of the year, so June of 2020, and said, all right, if we were to model a grid that's 90% renewables, what would that look like? And they're assuming that they have some pumped hydro, but so that makes it a lot easier to get to 90% because you've got an awful lot of water. You can raise up and down an incline elevation. You lose 30% of the energy in the round trip, but you still would have it available. Versus lithium ion, where lithium ion batteries are around 90% round trip efficiency, you might lose another 5 to 10 if you have air conditioning requirements. So here we're looking at a year, 15 years from now. And what you can see is starting in January, the black curve is demand. That's the actual load. And I don't understand why the load drops so much in July. There's that one perturbation where it drops down. It's a function of the model. But anyway, what you can see is the gray is curtailment. In other words, solar and wind are so cheap from a upfront capital cost basis, you overbuild, and that's already happening. You basically say, okay, it's going to cost me X to build this. The fuel's free. My operations and maintenance is not really a function of how much fuel I'm running through the system because it's a passive system, right? Wind is a little more active, but still. And so basically we overbuild because we want to have as much energy as we can to serve that peak in July and August. That's where you see the supply and demand curve almost meet. So lots of curtailment, especially in the shoulder months, March through May, and then November into December. because you overbuild to meet that peak in the summer. Then the next thing is the solar. And you'll see there's basically, that's the light green there. And you ask yourself, or I did, how come the solar is higher than demand? Not curtailed, but solar generated. And that's simple, because it's charging the battery or the pumped hydro. So essentially, if you look at the next piece, it's the wind. So solar, obviously, it's a thinner sliver, January, February, March, tends to get thicker in the summer with more energy output because you have sun higher in the sky, longer days, right? Then the wind tends to be more of a winter phenomenon in many parts of the country. The wind is stronger in the winter. And so it tends to skinny down a little bit in the summer. Then below that, in the orange, you see your battery discharge. And essentially every single day, your battery is being charged once or twice, depending upon what's happening with the wind and the solar, and then discharging at other times of the day to meet your peak demand. And below that, you have your pumped storage, your hydro. And then the critical thing where you get your 10% fossil fuel is you're still burning natural gas. That's still your long duration storage. It's in the form of gas right now. That's essentially balancing off what's producing the majority of your energy, which is the wind and the solar. And so to decarbonize the grid and get to 100%, right now, the idea is we need to turn that CH4, that methane, into H2. And that's the new frontier right now, where the planning and the hundreds of billions of dollars is, how can we make that happen? And so Mitsubishi just sold its contract for its first 3 turbines that are hydrogen compatible in the United States. And GE announced a project, a 400 plus megawatt project starting, I think it's next year in Hannibal, Ohio, where they start with 10% hydrogen. And by 2030, they expect it to be 100% hydrogen. And Mitsubishi now has a 40 megawatt turbine that can burn NH3. It can burn straight ammonia. So starting to see a lot of technical progress in that space. When I talked to the guys in GE, they said there were some real interesting challenges with hydrogen, because any of you who've dabbled in the space know that the flame speed is different, that the speed at which flame moves across the gas is different. And then obviously, well, there's issues like embrittlement. 10% or more gas moving, hydrogen moving through a gas pipeline embrittles the steel. And then there are saturation points. You can get the atmosphere saturated with, I think it's 70% hydrogen, and it can still catch fire, versus natural gas, which is in the teens. So it's a more volatile gas to deal with for a number of reasons. So when they build the turbines, they had to completely change the geometric configuration of the nozzles that feed the gas into the system. And they had to first figure out how to mix natural gas with hydrogen, and then how to tweak those mixes over time to get from the 10% they're planning on right now to the 100% they expect to get by 2030. So there've been some really interesting technological challenges, which they've been working on down in their facility. They have a lab down in a big industrial facility down in Georgia, where GE's working on the hydrogen mix. And basically what they also said was, if you want to decarbonize your energy economy, you have to think about it. You either take it all out in front in the form of, say, hydrogen through electrolyzers, or you take it all out on the back end through carbon capture and storage. But if you take it out on the carbon capture and storage on the back end, let's say you're still burning natural gas, you still have over 15% emissions up front through the drilling, and especially from fugitive emissions, leakage from the entire system. And so if you really want a clean system and you want to get rid of all the greenhouse gases, and CH4, methane is about 80 times more effective at trapping the sun's heat in the first 20 years of its existence, and roughly 23 times over the lifespan of both gases. You've got to get methane out of the system. And so that's the thinking right now is, all right, we bring hydrogen in. Then the question is, can we get the electrolyzer cost low enough? First, the renewables low enough, then the electrolyzer cost low enough. Then how do we handle the issues around transportation and storage? And so the liquid organic compound approach is saying, we'll put that into this medium and we'll ship it. And then there's other ways, for example, ammonia. So lithium organic hydrogen is a fascinating approach. It has some real advantages. And I can't speak to this nearly as well as our expert on the call. The ammonia piece, though, is really interesting because while we don't have an LOHC ecosystem, yes, we've had shipments from Malaysia to Japan. It's starting to build up. The ammonia ecosystem exists all around the world. Every agricultural economy, which means every developing country, in this country here, not in the United States, we have two ammonia pipelines right now. And we deal with ammonia and fertilizer every single day. So one of the companies that I talked to, Gencell, is teaming up with TDK. Some of you might remember when we were kids, the audio tapes, Maxell and TDK, same company. They said they could make one of those like every 5 seconds or something. Well, now they're teaming up with this Israeli company, Gencell. And Gencell's idea is they take a fuel cell that can deal with ammonia. And their model is you basically build these fuel cells and a cracker. The cracker basically breaks. It's a fuel cell essentially that has a cracker that breaks the ammonia, the NH3, into nitrogen and hydrogen. Then the hydrogen goes into the fuel cell. And their idea is every truck stop around the world, you basically, if you were using fuel cells, you come up, there'd be an ammonia tank there, and then there'd be a cracker on site that would separate the nitrogen and the hydrogen, and then the hydrogen would go into your fuel cell. So that's their model. So there's all these different competing ways of thinking about how this hydrogen economy could unfold. And the interesting challenges are there, and what we see with batteries, for example, and we saw this with solar panels. Some of you might remember Solyndra and that whole thing where the conservatives really went after the Obama administration for the lost money on those grants for Solyndra. Well, it turned out grants also went to Tesla, and that whole program was profitable if you looked at all the companies, but they wanted to cherry pick the failure. Solyndra was a great technology. It was a cylindrical solar resource that could absorb the sun's rays from different angles. It was pretty efficient. It had a lot of potential, but it died on the vine because it couldn't compete against the economies of scale coming from poly and monocrystal photovoltaics coming out of China. With these 1 gigafactory in China produced last year more panels than the United States installed, a single company's gigafactory. So if you're a startup and you're competing against, if you're a battery startup and you're competing against this massive gigafactory ecosystem that's building out so rapidly, you could have a way better technology and still fail just because you won't take root in fertile ground. And so one of the concerns in the hydrogen space is because the nitrogen ecosystem already in the ammonia ecosystem already exists, that it may have a leg up on some other competing technologies that may be better just because it already has scale and investment and people who know how to do it. And certainly lithium ion batteries are by no means the best technology for what we're trying to solve for in the power grid, but they're so bloody cheap because it's the tick that rides the electric vehicle industry dog. And so the better technologies, there's a great MIT paper just showing how the other technologies get pushed to the side of the road because they cannot compete with this juggernaut. So just some things to think about. Last couple slides. This is getting to that 100% renewables penetration where it's pretty easy. This is 0 on the left, 100% on the right. This is Rocky Mountain Institute. They do some really great work in this saying, when you're down at just a couple percent renewables, you can use 5-minute spinning load following batteries, then, short-term spinning reserve, all that stuff. You don't really need a lot of batteries to do that. But once you get to where you need 2 to 12 hours a day, once you get to 50% of the power grid, that's what you need for that. You need to start to be able to move around larger chunks of energy. And when you want to get to 60 or 70% or 100%, now you start to have to move energy from one day to the next, because it could be that you have an atmospheric river in California and it's cloudy for 5 days in a row, so your solar panels aren't producing. So now you've got to have the ability to shift that energy from time A to time B. And then ultimately, if you want to get to that 100% and get rid of that blue sliver we were looking at before, which was that gas bubble in that 90% grid, then you need that long-term seasonal balancing, which right now looks like hydrogen. So that's the big picture. And then, the last slide, I think it's my last one, is, go all the way down here, This is DOE just put out a hydrogen roadmap last year, and it's definitely worth a read because it breaks the industry out into all the technical challenges from the electrolysis to the storage and the shipping, and then the combustion in a fuel cell or in a turbine. It basically lays out the steps and the challenges that have to be overcome across the whole ecosystem of hydrogen. So it's a really great piece, just if you're not in the space and you want to expose yourself to some of the thinking, it's a good primer to sort of look at what's state of play right now, where this is headed. Okay, so that's essentially the end of my presentation. We still have roughly a half an hour, so ask away.
Peter, if you want to stop slide sharing?
Sure, happy to.
I always feel after listening to your presentations, I have to run for a Tylenol to help me absorb all of what you have poured at us over this period of time with your tremendous amount of background knowledge. It really is always impressive. And each time I pick up something else that sticks. So yeah, as Ray was just doing, many rounds of applause here.
Well, thank you. My family says every time I speak, they have to run for a Tylenol. So we're doing okay here.
Well, we'll get you an endorsement sponsorship from Tylenol. By the way, my copy of the book was ordered months ago. Amazon recently told me that I might be seeing it shortly, so I'm looking to fill in all the rest of the gaps that I need to understand and be able to absorb it at my particular speed with a highlighting marker handy to keep marking things as I do that. So those of you who might be interested in going deeper, Peter's book is available on Amazon. It will officially be on the street June the 15th. Peter, for a starter, and I'll just kick one off, then everybody else can pick up. What percentage of renewable energy are we at approximately in the US right now in terms of percentage of peak load in some way, if that's a reasonable measure?
Yeah, I think the more reasonable measure is what's the percentage in terms of raw energy, because at the end of the day, it's the greenhouse gas emissions you want to get rid of, right? And so that's a function of just the terawatt hours. Because you see in places like California, where California actually hit, what, 90% for 4 seconds or some number like that a couple of weeks ago. But on average, it's not close to that. But again, Kauai, 50.8%, all the islands together are in the 40s now. As a nation, we're in the low 20s, but about 10% of that was hydropower from the works, BPA and the stuff that was built during, a lot of it from the 30s to the 50s, right? The big government projects, the stuff that if you read Mark Reisner's Cadillac Desert, which is just an amazing book. If you haven't read Cadillac Desert and you want to understand US water policy, and then by extension, agricultural policy and electric policy, it's an unbelievable book. And talk about an on-ramp. He talks about Wesley Powell, the one-armed veteran from the Civil War, making the trip down the Grand Canyon in a wooden boat, and makes the reader fall in love with the Colorado River. And then essentially the rest of the book is about how we completely massacre that river and dice it and slice it into a million little pieces. But back to the original question. So the Pacific Northwest is huge in hydro, right? They're taking down some of those dams now, but that's, I think, roughly 10 or 11%. So now we're about equal to that with the wind and the solar. But the wind and the solar are really picking up speed, so that last year, more than 50% of new capacity added into the system was from renewables, from the wind and the solar. And those numbers just keep getting better because fewer and fewer players are willing to take a risk on gas. And this concept, it was called the gas bridge. The idea we'd move away from coal, build this bridge of gas-fired turbines that would eventually get us to renewables. Now it's more like the gas crack bridge, because the concern is we addict ourselves, we make these multi-billion-dollar investments, 30 to 40-year assets that we then don't want to strand. So we keep burning gas because we don't want to shut down these facilities. And already, we're seeing that with American Electric Power with coal. They know it's bad, everybody does, but they're still running these things because they don't want to shut them down because they have these stranded cost investments that the ratepayers would have to pay. So that's the real critical piece, is how much new stuff do we not build that's either going to addict us to consuming more gas in the future, or it's wasted capital.
Kevin, I'm curious, were you aware of the project that Peter was talking about in Australia with those battery-sized refrigerators in a residential development?
No, I wasn't actually. I'd be interested to know whereabouts they actually are. They might even be in the suburb just down the street. So whereabouts were they, Peter?
I would have to look. You know, I find a lot of times I forget a detail, and I like, oh yeah, I wrote about that 3 years ago. So then I Google my name and the title and Forbes, and then I pull up all the information. And I have it again. So I could find it again, Kevin. And if you shoot me an email later, I'd be happy to tell you and give you more details on it.
Thank you.
I have a follow-on question about Australia, if I may.
Yeah.
I think I heard you say that the price of power sometimes in Australia is very, very, low, sometimes negative. Does that mean that folks in Australia don't need to put up more solar panels on their roofs? Is that what I should understand, or no?
It means that the economic incentive is declining because the more people that jump into the pool, the dirtier the water gets, right? To use a very unsavory image.
Yeah.
But if you could then add 4 hours of batteries, now basically you can stick that energy anywhere. So then it becomes inherently viable again. So that's the real dynamic around the integration of more renewables right now. Really has to do with how much more storage is added to the system, because that's the enabler that essentially takes us and lets us go from, say, a 30% to a 60% regime. But yeah, right now, and the way power markets are priced is every single hour, it's an auction, right? So the ISOs, the grid operators, whether it's Australia or in a competitive market here, say, how much demand do we think we're going to need? In fact, they do it. They say, how much demand are we going to need between 12 o'clock and 1 o'clock tomorrow? And they forecast an amount, and then suppliers bid in. And where the quantity of bids hits the quantity of expected demand, whatever that last bidder is that gets accepted, that's the marginal price for everyone. It's the classic price of butter or anything else in economics 101. The problem is, if you have zero cost resources bidding into the system, there's a very different view of what your marginal cost structure is. And so there's been this softening of prices, especially when you have a surfeit of solar, and then you have a whole bunch of gas-fired generation that doesn't want to go into cold start mode because they know what that cost them. So they're willing to spend negative dollars to keep running because that's cheaper for them than shutting off entirely. So now you come up with what we economists like to call perverse economic outcomes, right? Where 5 hours a day, prices go negative, and that's kind of a weird thing. Although we also like to talk about short-term equilibrium versus long-term equilibrium. And in this case, as an economist, I would say, assume a battery. Because when you have those kind of price dynamics, in no time, somebody will bring a battery to the game because that arbitrage opportunity becomes so clear. Then the question is, how many batteries come into the system? When Tesla threw its Hornsdale project into Australia, it was really cool. The grid was super unstable, and Musk, being the P.T. Barnum showman that he is, basically tweeted in September, I think it was September, it's late in the year, said, I'm going to put a 100 megawatt battery into the Hornsdale Reserve as a wind farm that had really unstable grid conditions. Said, if I don't put it in by end of the year, by New Year's, you can have it for free. So it was the largest battery resource in the world at the time. It got built before Christmas, but what it did was, it so stabilized prices for a while that it crushed the opportunity for anybody else to come into the system. And so, if you're a developer, you really have to be looking around going, okay, what's the equilibrium today? But what would it look like if someone else gets there before I do? Or what does my actual investment do? Because I might ruin my own volatile pricing environment just by virtue of being there.
Can I ask a question?
Sure, please.
You were talking about the crowding out and effectively of innovations. That's really worrying, isn't it?
Yes, it is.
What would you like to see happen, and what could happen, you know, to rebalance that, to make sure that those innovations can still be nurtured to the point where they should be able to contribute and compete?
Well, if we move from free market to a market that actually would effectively serve people, the first thing we do is we internalize the externalities, right? Pollution shouldn't be free because it means other people bear it. It's a cost, but it's hidden in medical bills and everything else. So the first thing you do is you'd start to put a price on pollution, right? Then what you could do with that money, and this is what's happening in places like New York, they're thinking about putting a carbon tax, a price that you'd actually bid in. Barry, if you had a coal-fired plant or a gas plant, you'd have an adder on that plant. And so if your resource got selected, let's say it cost you $30, you'd have to bid in at 33. If you got selected at 33, that's the clearing price, you only get the 30. The 3 goes to subsidize clean resources. If governments were smart and they had this long-term view in mind, and I've been actually pretty impressed with the team on the Biden administration. There are a number of my colleagues that are now working in that space. And what they're looking at, DOE, for example, Department of Energy, is long duration storage. And they're trying to create mechanisms to fund the research and subsidize the outcomes, which is what happened with solar. I mean, the only reason solar is where it is today is because way back when Germany said, we're going to pay a feed-in tariff. Anybody who puts solar on the roof, we're going to treat them like they own a power plant on the roof, because they do own a power plant on the roof. And we're going to pay them roughly 44 cents a kilowatt hour, I think the price was. Yeah. And so it got so big so fast that the Chinese said, oh, we now see a market with scale. And so they bought Q-Cell and a bunch of the other German companies, moved them down to China and started volumetric production. Then the US got into it, Australia got into it, and suddenly there's this global market. But it all started because one nation state said, we are going to subsidize this industry and make it grow. You could do the same thing with long-term storage or a better storage technology.
We followed, I'm pretty sure, with feed-in tariffs, although they've kind of declined now.
Yeah, I remember you did.
They've done their job. But what should the rest of the world, what should the UK be doing in that case?
Yeah, and UK's got a really great, robust storage. But again, it's I think what you do is, first of all, you look out and say, what do we need 10 years from now? And it's clear that the lithium ion is going to cover the 4-hour range. But the problem is it then essentially rips the guts out of that whole market for those longer duration storage, where they've taken the nicest part of the market and stole, they've taken the frosting off the cake. So I think what you've got to do is you've got to create some kind of an incentive mechanism that says, if you can offer a storage from 4 to 12 hours, we know we're going to need it in the marketplace because we don't want gas turbines doing that. We will pay X for that resource. And it could be like, in here, we have a production tax credit for the wind. Every single kilowatt hour of wind that's generated gets 2.4 cents a kilowatt hour. Now, it's a market distorting thing, because if the market price is 0, I can still bid in, make no money, but I get my 2.4 cents per kilowatt hour incentive, right? So you have to be really thoughtful about how you do it. But I think that's a critical role for government. If the role of the government is to protect its people, then arguably the role of the government is to protect its people from the uncertainties and the economic damage that will accrue from climate change. And therefore, it's just like an investment in weaponry. It's another way to keep us secure, albeit a more healthy one. So we should think about investing and subsidizing those technologies in a very similar fashion.
I'm going to write that down, Peter.
What?
If it's the job, I'm going to write that down. If it's the job of governments to protect its people, it's the job of governments to do some of these things. That's brilliant. Thank you.
My pleasure.
Peter,
The blind acorn, is squirrel finds the acorn, right? Yeah.
Peter, let me just, for some of the people here, make them aware and pick up on a point that you were just making in terms of potential subsidies for storage. And that is that Dr. Pez Guido here on the screen, who's leaning in to listen to what we're saying, has applied for patents that will store will release renewable energy from a liquid organic hydrogen carrier, DBT in particular, and that there's a company called Hydrogenious in Germany that makes equipment to produce this liquid organic hydrogen carrier, which is the consistency of olive oil, and can flow in existing pipelines and trucks and tankers, etc. The challenge is, how do you get it out? But it can be the storage mechanism for renewable or green hydrogen if everybody can make the economics work. And the people who are working on the electrolyzers to create the hydrogen can pump it into equipment by groups like Hydrogenious. And then the question becomes getting it out. Well, right now you can still get it out as a gas, but that has impacts always on its cost. Guido and Energy 18H, the spinoff company that YARcce created, is working to create a fuel cell that can take it through as a liquid and not have to regasify it again. And Energy 18H has been getting some considerable interest. We're keeping our fingers crossed that some major dollars will begin to flow in the next months. And they were talking about the UK, are in conversation with a UK venture fund that also has an interest in Hydrogenious and want to, introduce people to people in addition to potentially helping with the work that Guido and Kai Langstrom and others are working on. So it's something that we want to help promulgate and also get into the political mix. And I've been talking lately to starting conversations with some of our political leaders for them to realize this is something that we're going to need some help on. And I may need you to testify at some point. I'm reaching out to our former Congressman, Charlie Dent, who's become famous because he's been objecting on CNN to Trump on occasion. And he used to head the Hydrogen Caucus, because here in the Lehigh Valley is Air Products, where Guido used to work, and a number of other people, and they are, big into hydrogen. So I'm listening carefully to those political implications and how we put words out there to get political support in a variety of different ways. But I think you're making the case that hydrogen has to really be focused on, and you're providing the data to why it is the seasonal storage and the time shifter for renewable energy when the wind don't blow and the sun don't shine.
Yep. Yeah, and I mean, you talk to people like the CEO of 8 Minute Energy, and he's one of the largest developers of renewables in the country. And he basically says, this stuff is going to be within the next decade down below a penny a kilowatt hour, just in wholesale markets, right? We're already seeing Saudi Arabia did a 1.04 cent deal a couple months ago. So renewables almost are going to be free in some areas because they're just so efficient. We have good sunlight and so on. So then the whole game shifts to assume a nearly free fuel now, but it's variable. Now, how do you move it? How do you store it? How do you apply it to the economy? And the other critical piece is it's not just the electron. A third of our emissions, the GHG emissions, are industrial, with 8% of that from steel alone. So we need to figure out how to take the electron from renewables, turn it into hydrogen, and then apply hydrogen to industrial applications in the form of heat or other ways to essentially drive carbon out of that part of the economy as well, which is another reason hydrogen is going to be so critically important. In fact, there's a company called, SAB, the Swedish steel, SSAB. They're responsible for 10% of Sweden's emissions, 7% of Finland's. They have a facility up in Luleå, north of the Arctic Circle in Sweden, called Hybrid, where they're making sponge iron from hydrogen. And then that goes into a clean electric arc furnace, 100% electricity, clean electricity. So now you have carbon-free hydrogen. And Volvo's already said they want that for their chassis, for their cars. So you're starting to see some first inklings of, oh yes, this is technically feasible now. Can it be economically feasible?
I'd like to follow up on some of the political stuff that's been raised. I live half my life in Spain, and the Spanish government, for reasons that I totally fail to understand, has made it illegal to sell electricity back to the power grid. And the only reason that the obvious reason would be that the boards of various electrical utilities are the favorite retirement place of Spanish politicians once they're out of office. But I'm wondering if there is any, from your point of view, is there any rational or perhaps technological reason why it would be interesting to not permit that to happen, or is it just what it seems to be?
So the answer is in two parts. If you were the first person putting solar on your roof, the answer is there would be no legitimate reason to deny that, to sell it to the grid. The question would be how much you're getting compensated for. In the US and 42 states, we have what's called net energy metering, where if you sell a kilowatt hour back, it's accredited on your bill for all the costs on your bill, almost all of them, not just the energy, but distribution as well.
That's how it works in most of Europe, yeah.
Right. So the challenge with that is take that to its logical conclusion. I'm the last guy that heard about solar. So every other person in my whole utility has solar on the rooftop. Let's just, again, economists, assume everybody has a south-facing rooftop and the money to do it. So I'm the last guy left. That means everyone else is essentially zeroed out most of their bill. They still want the wires and poles. They want the grid to serve as a battery. When there's an outage, I still want some lineman to climb up and reconnect me, all the stuff, right? Send me a bill, track all my consumption, all that. When you get to a certain level, it starts to hurt from just a revenue perspective. So there's that sort of self-interested economic piece. We do want our utilities to continue to be viable. The next piece is once you get somewhere around 10% of saturation, you think about it. If you're sizing your rooftop in a net metering perspective, so that you're essentially zeroing out your bill for the year. That means during April, May, June, July, and August, you're trying to produce power that covers nights and winter, right? So you're exporting in the middle of the day, just a ton of electricity back onto the grid. A lot more than just not consuming during that hour. It's multiples, right? In order to balance your bill out for the year, and that's the game. And so HECO, for example, Hawaiian Electric, they had so much bidirectional flow on a system that's only designed for one-way flow that at some point they said you're destabilizing the grid. And among other things, we have to start to move intelligence down into the feeder level to know what the heck's going on. And so at some point they said, we're not taking any more solar only applications. You can't export power back to the grid unless it's after 4 o'clock in the afternoon, which de facto implied that new people had to put a battery on the roof. And that's in fact what has been happening in Hawaii. So now there's 80,000 customers that have solar on the rooftops, and then a ton of them have batteries. And in Maui, where I was telling you about the 50.8%, I think 22% of what they say is renewable is customer side of the meter. So it can be done. There's definitely some value, especially in the early stages. You can reduce some of the cost for the utility, but there is a tipping point after which the costs start to get higher. Places like Minnesota do this thing called value of solar, where every year they look at what's the cost and benefit of adding a new unit of solar into the mix versus last year, and then say for new ones, this is your new value because this is now how much we've established the benefit cost analysis is.
So what if we were to go one further maybe than the use case you showed from Australia, and where you would say take a group of houses or individual homes or a neighborhood and disconnect it from the grid, make them self-sufficient. Probably it would be more reliable if we used more low voltage equipment where it was possible, like for lighting and for refrigeration and so on. Probably can't do it for a washing machine, but stuff like that. And use the grid primarily for those industrial applications that you were talking about earlier.
Yeah, you'd want to do DC, but yeah.
Yeah, okay. And so, does that seem like a viable way to go, or is that maybe pie in the sky?
So it's a really interesting question. And there's sort of two terms of art. One is grid defection, which is what you're talking about, right? The other one's load defection. Load defection is what's happening now, where I take 80% of my consumption off the grid because of my solar and my battery. So, but there's a great story that just came out last week where this guy in, I think he's like North and South Carolina, his property sits on 2 different utility jurisdictions. And so he couldn't get, he had to petition his neighbors to string the wire across their properties and they wouldn't do it. So finally it's like, forget you guys. And he had enough money. So he basically put solar on the rooftop and enough batteries. And he said, I'm not doing this thing where if I have 3 kids with long hair and 3 800-watt hair dryers, they can't all do their hair at the same time. He goes, I'm going to the max. And so he has created his own little nano grid and he had enough money to do it. Now, today we put our nano grids, every ship is a microgrid today already, right? Every camper is a nano grid and every off-grid cabin is that way. As the cost of batteries come down, what you're talking about becomes more feasible. And think about this. So every electric vehicle that rolls off the lot today, purrs quietly off the lot into the marketplace, lasts for about 10 years. When that battery's done, the first batteries that have been out there that long show that there's roughly 80 to 90% of the life left on that battery. And yet they're fully depreciated and they're coming out of the car. And there are already companies now that are going to put software in that monitors those batteries during its whole life so they know how good that cell is or those cells. These things are likely to come into the market at 20 to 30% of today's prices. And there's a whole bunch of companies that are already gearing up to repackage used batteries. The analogy I use is there's an earthquake today, which is the car rolling off the lot. The tsunami comes 10 years from now. So whatever volumes we're seeing today, which will be 400,000 cars in the US if the Q1 numbers hold, those vehicles, all those batteries, gigawatt hours of batteries start to flood into the market. Some of them will be recycled, but a lot probably get repurposed. If those become super cheap, what you're talking about becomes inherently more feasible. And yeah, you might back it up with some propane tanks just to solve for, system peak within your little microgrid. But especially if you could find complementary users that use power at different times of the day. If you're only sizing for 1 or 2 or 3 homes, it's a lot more expensive than using the grid as a battery. But if you start to size it for larger groups, the ability to start to island off and in fact defect from the grid entirely becomes possible.
Peter, I think we're at the point that I'd like to stop and your presentation and let you get some feedback from the people who are here because we're beginning to lose people time-wise. If it's okay with you, let's see if people can say, what they heard, what they found interesting, and what they're maybe even struggling to understand, just to give you a little bit of a sense of that. And Guido, how about popping in here? I'm sure you've been ready to say something for a while.
Yes, I am. I'm thinking of the situation of so-called long-term storage. If one imagines that a company has a device or whatever that can take the electricity from, let's say, 1 month and hold it, store it in some way, and deliver it in the 2nd month, which is consecutive. The economics problem, which really you alluded to, is that the company will only get paid for the electricity that it delivers back to the grid of the consumer. In other words, it will only get paid for half of the time for which it has invested capital. So that's the fundamental problem that you actually referred to in answer to one of the questions. And your answer was, well, the only way to overcome the 50% decrease in cost in terms of capital and other things is for the government to recognize the value of longer term storage in terms of health of its citizens, et cetera, et cetera. But is that it? Is there no other way?
I mean, you could let market prices, if you put a high enough carbon price, for example, then that would help solve the problem. Otherwise, the challenge is you would need to let prices go really, really high to reflect the scarcity of clean energy resources during those hours, for which the hydrogen would be required. There is sort of an analog for that in the sense that Texas lets prices go to $9,000 a megawatt hour when the average price is 30. So there is a possibility a wholesale market could be structured to do something like that, but it'd be a pretty heavy lift.
Yeah, but it's always going to be more difficult, always more expensive. As in
Yes.
our case,
Yeah.
the energy is stored in an organic liquid. It's the cost of the organic liquid that is
Right.
going to be. But the beauty of it is that versus batteries, you're storing the energy in the organic liquid, and that's all. But of course, you still have to factor the cost of the energy that you require to recharge the organic liquid, and the cost, of course, of releasing the energy from the organic liquid. But at least in contrast to batteries, okay, which are the cost is multiplied by the device. It's the whole device that's of course the capital. In this case, it's only a smaller part of it, which is the fluid, which is where the energy is contained and stored. And okay, so but fundamentally, the economics still suffers from the fact
That's a challenge, without question. Yeah.
and that you're only getting money back during half of the time. Right?
True.
Okay, thank you.
Kevin, I'm curious if you have some thoughts or comments since you have spent so much time looking at renewable energy.
Yeah, I'd like to get your thoughts on pumped hydro, and you hardly mentioned it as a storage mechanism, and yet it does seem, well, what's the future for pumped hydro?
Yeah, so the challenge with pumped hydro is, first of all, it's a function of three things, right? The volume of the reservoir up top, the head, the elevation, and then the volume of the reservoir down below, because nobody's doing open streams anymore, because you scour up, two things happen. The cold water from the bottom of the dam changes the thermal profile of whatever's downstream, and then the flows rip out all the benthic creatures and ruin, or at least dramatically change the ecosystem downstream. So you have to have a closed loop system. Now the challenge is these things take about 5 years to build, and they're generally, say, $1 billion for 500 megawatts, and then depending how many megawatt hours. I mean, bigger reservoirs, awesome, because the bigger the reservoir, the more energy you have to solve the problem. The other challenge is you do have around a 70-75% round trip efficiency. So there's a fair amount of loss in the process of pumping up and down. So long lead times, environmental issues, because you got to find places like that. And then the issues around the round trip efficiencies and the high capital costs up front. The thing that scares a lot of people now is the world's changing so fast that you can invest in something. I mean, think about the solar industry. It didn't exist 10 years ago at any scale, right? So I'm going to put $1 billion into something that's going to take me 6 or 7 years to build, all kinds of permitting, environmental fights with everybody in the world who hates me, and the whole world could have changed in 7 years. It's a risky proposition.
Yes, but the hydro things, they last for hundreds of years.
They do. Yep.
So is it just simply a fact that we actually worry about the short term as opposed to the long term?
In the sense that we're not willing to sacrifice anything environmentally, whether it's a lithium mine in Nevada or a hydro facility in some place in the country where all the folks who live nearby are fighting against it. But I'll also tell you, 3 years ago, Sacramento Municipal Utility District, their CEO was speaking before me at a conference, and he said that they had threw away about $20 million of planning because they were looking at this $840 million hydro project, and then the world changed so much, it didn't fit what they needed anymore. So those are the issues that are of greatest concern. But yeah, if you could build them tomorrow and there weren't environmental issues, I would say that would definitely get you as a critical storage resource to get you to the 70 or 80% thing, which is like Kauai's doing a pump storage. And it's going to really help them hit that 80% mark. So right places, right ecosystems could be a good solution, just very limited in terms of the solution set where it can be applied.
And the other one that I was interested in is the shifting heat. Using buildings as a way of being able to shift the energy pattern, and how much do we know about how much thermal storage an average building has got that we can use to move our consumption from the daylight hours to the nighttime hours and so forth.
Yeah, so thermal masses. Yeah, I used to play in that space a lot as head of demand response because I wanted to turn every building. We said we're going to turn your building into a battery. What we found is there's a couple critical pieces. First of all, most buildings are not owner occupied. They're triple net lease. There's a real estate holder that doesn't hold them for that long, is usually looking for appreciation of value and into flipping. The tenants pay for the spaces they rent. The owner pays for the common spaces. So if you change temperature set points, for example, in the tenant space, now you're messing with the comfort of the tenants. So what we found was it was pretty easy to create a value proposition that said, we'll pay you X to use the thermal mass of your building and change the temperature set point from, say, 68 to 72 degrees and let the building drift on its thermal mass for the next 4 hours. That was no problem, especially if it was towards the end of the day. If people leave at 5, nobody cares. But if it's in a space that a tenant has, the landlords are like, you are not getting anywhere close to potentially infringing on the comfort of my tenants. So it was a very heavy lift. It can be done, but you know what's much easier? Throw a thermal battery in the basement. Like in the whole southern half of New York City after Superstorm Sandy, there was a company that Train, the air conditioning company, had bought another company, and they put these massive ice tanks in the basement. Rockefeller Center in New York City has huge ice tanks in the basement, and they make ice at night, and then they feed that into the AC system during the day, and it accomplishes exactly what you were talking about in a much denser profile with clear economics and no sociology.
Thank you.
All right, we have run past our time, and I don't know, does anybody have something so burning that we need to do it?
One question.
Matthew, you haven't had a chance to talk yet?
Yeah, thank you so much for your talk. You talked about the technological aspects of innovation. I was curious about, actually, you were just talking about it. It's hard to go from 72 to 68 or vice versa. Yeah. The capacity for human change. And I was wondering how much fat or waste is in the system. And is there any room to reduce our demand there? But the second part of my question would be, who in the public arena is speaking to these issues to your delight that you can shine a light on?
Politicians or?
Both leaders who are trying to educate the public about what's going on. It seems to be kind of empty right now.
Okay. Yeah, you know what's interesting? One of the reasons I wrote the book, here's this multi-trillion-dollar transformation. Name me a storyteller. Like, you know, if you want to know something about astronomy, it's Neil deGrasse Tyson, right? If you want to know about this thing, you know who the people are. Here's this thing happening, and there's almost nobody trying to make sense of it to what, I mean, I'm just trying to make sense of it to fellow practitioners, first of all, then, you know, trying to talk to the general public. There's a really great group called Canary Media that just spun out of Green Tech Media, and Dave Roberts, who used to write for Vox, he's to my mind, he is the best storyteller in the industry of taking complex stuff and writing it about it, where he'll even in his paragraph he'll be like, whoops, or what was that? You know, like he mixes it up. He makes it very approachable. So he's really good. In the public arena, the folks, I mean, I really like what Jigar Shah is doing. He's now heading the government investment stuff. He founded Sun Edison and then was Generate Capital, and he's a very opinionated, smart guy. And now he's heading up the loans. Kelly Speaks-Bachman, who used to be a former colleague of mine, then a Maryland commissioner, then headed up the Energy Storage Association. She's now the Undersecretary for Energy Efficiency and Renewables, and she's super bright. And what's coming out of there is pretty intriguing. So I've been very impressed with what's coming out of the Department of Energy, and then the understanding that technology is not the whole piece of this thing, but it's a critical part. And if you want to get both parties along, one party's more focused on pushing this thing hard, and the other party's more about the economy and innovation. Like, to grab the Republicans, you got to really show what's in it for us, what's in it for us, what's in it for us. And I get that. And I think they're starting to pitch the arguments more that way. And as someone said last week, another journalist, I can't remember who, you want to get people to adopt clean technology, make it great. And that's what Ford F-150 just did, right? You got to make it better than the thing was. We're not going to freeze in the dark with sweaters on. It's just not humanity is. We can say I love our children, but we apply a discount rate of at least 6% to their well-being in the future. So we don't really act as if we love them as people in our functioning economy, if we call it that, right? So already I know that humanity, for the technical word, we suck as people who love the next generation. We don't act that way. So now the question is, can we create an economy that acts as if we do love them by changing things a little bit? I've given up on people, but I still think markets can work if you structure them the right way.
All right, thank you.
Give it up.
Barry, come in here, but
Yeah, I'll be very brief. In fact, I'll be brief. I don't know whether Peter can be.
I can't.
Yeah. Look, I'm in the north of England right now. I come from the north of England. It's full of holes. We dug all these great, you mentioned mines before. Yeah. How does that compare in terms of investment and in terms of yield and all of that to other storage technologies? Are we sitting on a gold mine, coal mines, or is it, something else?
So do you know the port of Speith, S-P-E-I-T-H? I think it's in Scotland. Gravitricity just started testing that weight thing. And the idea is to find those abandoned mines and use them everywhere, right? Because someone else already dug the hole. So there's something that it's again, can they do it at scale? But yeah, you could be sitting on a potentially empty gold mine that still has value.
Great, thank you.
Yeah, my pleasure.
Peter, thank you. This has been fantastic. If you just saw Ray's comment in the text, it has been kind of mind-blowing, as every time it has been when I've experienced your presentations. I look forward to having other involvement with you in the future. I thank you for bringing up all kinds of real practical and economic kind of issues that need to be solved. And those of us who can help get the word out here, hopefully we'll put the word out. And yes, many rounds of applause. Thank you, sir.
Well, thanks for the, as you can see, I love the energy conversation. And Barry, no, I can't give you a short answer because everything has to be contextualized. But thank you for bearing with me. It's been a real pleasure, and I hope our paths cross in the future.
I hope so too. Thank you all. Have a good afternoon, everyone, wherever you happen to be, or next day where Kevin is already into Sunday. Enjoy Sunday, Kevin.